Hey guys, hope you're doing good, and in this video we're going to be taking a look at k-means clustering. To start off, we're going to create some unlabeled data, and then once we have the basic math and understanding of the clustering algorithm done, we can generate a much larger data set and then fit clusters to that data. So for now, let's get started with an example data set and introduce k-clusters to that. And as a quick side note, we're going to be using Jupyter Notebooks with NumPy, Matplotlib, and scikit-learn installed. So if you want to follow along, make sure to set up an environment like this one. Alright, now to get started with the k-means clustering algorithm, let's go ahead and create some example data. And in this data, we're going to use some example shirt sizes. So we'll have the width and length of different shirts. And then we're going to apply the k-means clustering algorithm to try to differentiate between large and small shirts. So let's go ahead and take a look at what that means. Alright, so here we're taking a look at a shirt. And this shirt is going to have some width to it. And then it's also going to have some length. And let's say we're looking at a few different examples of some different t-shirts. So those t-shirts would have all different sizes. Alright, so here we're looking at 4 different t-shirts. The first one has a width of 1 and a length of 2. The second one has a width of 2, length of 1, and so on. And let's go ahead and assign some variables for these two features. So we can say width is x1 and length is x2. And in the shirt column, we're essentially saying that each shirt has a corresponding 2 features. So one way we could put this mathematically is say we're looking at an x vector. And since these shirts are indexed going from 1, 2, all the way to 4, we can index them with an I. So let's apply that format to the column now. And for future notation, we'll say I starts at 1, just like here, and it goes all the way until m, which m is going to be the number of examples. In our case, m is 4. So we'll write up here, I is equal to 1 going all the way to m. And we can also notice that there's some set number of features. In our case, there's 2. But let's go ahead and index these features with the character j. And that's going to go from 1 all the way to n features. Now this notation is going to help us a little bit later on, but for now, let's graph these points right here so we can visualize the data that we're working with. Now just taking a look at this data, it's obvious that there's probably a cluster down to this bottom left and another cluster up to the top right. So one thing we could do here is create some cluster point at both of these regions. And then we could say for any given shirt width and length, the labeled size of that shirt can be determined by the closest cluster that that point is near. So for example, if we had a few more points, then we can obviously see that these new points on the bottom left are closest to this blue cluster, and the points to the top right are closest to this yellow cluster. And since we're working with t-shirt sizes, we might want to end up labeling these clusters. So this blue one could be considered small shirts, while the yellow one is maybe large shirts. So what we did just now is we kind of eyeballed where these cluster centroids should be. Centroids being this blue and yellow dot that we created. But mathematically, we can't just eyeball the data and then plot a point, especially if we're given a lot of data. So let's take a point at the k-means clustering algorithm, which will allow us to find these best fit clusters given our example data. And the first step to this algorithm is to randomly initialize the position of these cluster centroids. So let's go ahead and do that on our graph. Alright, so in this case, we're using 2 cluster centroids. And notice how these 2 centroids are not colored. That's just to say that they're not pre-labeled walking into our data set. They're just 2 points randomly plotted on our graph, where 2 is an arbitrary number. If we really wanted to, we could say 3 clusters or 4 clusters. But since we know this data for now, let's work with 2 clusters. And just like we did with our training data, let's mark the x1 and x2 positions of these 2 points. Alright, so here we have cluster 1 and cluster 2. Cluster 1 is going to be represented by this point, and 2 is represented by this point right here. And to avoid confusion, let's actually mark these points as a star instead of a dot, since our training data is already a dot. Alright, and to label the vector for each cluster, we can't use that x vector because that's what we're using for our training data. So instead, what's commonly used is this mu of k. So then in the cluster column, we can say mu of 1 and mu of 2. Now with these two cluster centroids created, we're going to want them to reach that final destination we looked at earlier, where cluster 1 and cluster 2 have a centroid in the middle of that training data for small and large. And to do that, we'll want to find the data points closest to each cluster, get the mean of those data points' positions, and then move our cluster to that mean. Or if we want to look at that visually, then if we looked at this first cluster right here and we wanted to see the data points that were closest to this cluster and not cluster 2, then starting with cluster 1, we can look at its distance from point 1, point 2, point 3, and point 4. And then we can do the same thing for cluster 2. So what's the distance between cluster 2 and point 1, 2, 3, and 4? And after comparing all these distances, we can see that point 1 and 2 are closer to cluster 1, and point 3 and 4 are closer to cluster 2. So now if point 1 and 2 are closest to cluster 1, let's take the mean of the positions of point 1 and point 2, which would lay somewhere right here. And now we can consider that point in between 1 and 2 as the optimal point for cluster 1 to be moved to in order for it to represent the small data as best it can. And we want to do the same thing for cluster 2. So since cluster 2 was closest to point 3 and 4, we'll want to move cluster 2 into the mean of those two positions, which would lay about right here. And this very closely resembles the points that we eyeballed earlier. So by using this algorithm, we can effectively figure out exactly where each cluster needs to finish in order for it to best represent the cluster of points that it's near to. Now let's write out what we just looked at. So we have cluster 1 is near t-shirt 1 and t-shirt 2, and then cluster 2 is near t-shirt 3 and t-shirt 4. Therefore, we want to update position of cluster 1 to the mean of t-shirt 1 and t-shirt 2. And do the same thing with cluster 2 against t-shirt 3 and 4. Alright, so now let's quickly summarize the steps we just took to find these cluster centroid positions. So first, we randomly initialized the cluster centroids. Next, we found the closest data points to each cluster. Next, we found the mean position of all the closest data points for each cluster. And we haven't mentioned this yet, but we'll want to repeat steps 2 and 3 until our clusters converge. And by applying these 4 steps, that will be considered a single attempt at finding the best clusters for our data. One other thing to note is by applying these 4 steps, we're not necessarily guaranteed for our clusters to be optimally placed. And that will make more sense later when we get into the Jupyter Notebook. But for now, we'll want to say we want to repeat these 4 steps repeatedly until our clusters find the optimal convergence. Now at this point, we can go ahead and jump into the notebook and start coding. Alright, so here we're back into the notebook, and just like we did earlier, let's initialize our X training data. And we can go ahead and use these same values we came up with earlier. So here we have the width and the length of each shirt. Let's plot that out. Alright, so here we have a plot that looks very similar to our whiteboard. We have width and length with each t-shirt represented as a data point on here. And now that that's set up, let's randomly initialize our centroids. Alright, so here we created 2 centroids. This top row is going to be the first centroid, and this is the second centroid. And notice how we used k to define the number of centroids, and n is going to be the number of features. So we're still going to have centroids in the width length dimension. And for now, let's go ahead and plot these centroids against our t-shirt sizes so we can see where they start off. Alright, so our centroids were represented by mu, so that's an orange, and blue represents our training data again. Now what we want to do next is find the distance between each x data point and each cluster centroid, and then move our centroids to the mean of the closest x data points. So first, let's write a function that gets the distance between an x data point, such as this one, and a centroid, such as this one. Alright, so here we have a function that calculates the distance between 2 points. And these points can have any number of features, meaning it's not bound to a 2D plot like this. It could be a 3D, 4D, 5D plot. So just checking out Google Images, we can find the equation for distances between 2 points that are plotted in any number of dimensions. Basically what we're doing is we're summing the differences squared at each vector element and then square rooting that completely. So if we implement that same distance function that we just saw, it would look like this, where for each element of 2 points, we're taking the difference squared, adding it to some final value, and then square rooting that final value. And with that distance function done, we can go ahead and figure out which x points are closest to each cluster centroid. So let's get started on that function next. All right, so here we have the start of a function for calculating the closest cluster centroids for each x data point. So we're going to have this closest array, which is going to be an empty array initially with the size of m, or the number of x data points. And each element in this closest array is going to hold some centroid index for each t-shirt in our data set. So for example, if this bottom orange point was the first centroid, or at index 0 in our centroids array, and this blue point was our 0th t-shirt, then we could say closest at 0 is equal to 0. Or in other words, our 0th t-shirt is closest to the 0th centroid. And let's say this point right here was our second index. So t-shirt at index 2 is closest to this 0th shirt still too. And if this was the centroid at index 1, and this is the t-shirt at say index 3, then t-shirt at 3 is closest to cluster 1. So t-shirt 3 is closest to cluster 1. Then at the end of this function, each element in our closest array should have an index of the closest cluster for each x data point. So what we can do now is iterate over each x data point and find its closest centroid. Alright, so here we're iterating over each x data point and initializing the closest cluster distance to some infinite value. And then we're going to iterate over each cluster, calculate the distance between our data point and that cluster. And if that distance is less than the closest distance, then we'll update the closest distance and set the closest cluster index to k. And once we do this for each cluster, we can determine the closest cluster for that x data point. So once we do that for each x data point, we can then return this closest array. So let's see what that closest array returns to us with this data set right here. Alright, so this gave us 1, 0, 1, 1. And again, these are the indexes of the closest clusters for each x data point. So if we have 1, 0, 1, 1, then I would guess that this is probably cluster 0, and this is cluster 1, where cluster 0 has this one data point closest to it, and then cluster 1 has all 3 of these data points closest to it. But instead of just guessing, let's try to visualize the closest centroids. Alright, so here in this function we have plot clusters passing in x, the centroids, and the closest centroids for each x data point. And then we're going to scatter the x data points and the centroids. The data points are circles and the centroids are stars. And then I went ahead and manually created the legend so that we can have these markers as black. And just like we predicted up above, the closest point to this blue cluster is this data point right here. And then the cluster closest to the rest of the data points is this red one right up here. Now in our next step, we want to find the mean position of these closest data points and move the clusters to those mean positions. So let's write a function to update the centroid positions now. Again, we're going to calculate the mean position of the closest data points for each centroid. Alright, so here we're iterating over the indexes for each centroid, and then we're going to count the number of data points that are closest to that centroid. So for example, this blue one would have 1 data point, and the red centroid would have 3 data points. And then we want to sum up the feature values for each x feature. And then to get the mean, we'll divide the sums by the number of data points closest to that centroid. And to avoid any divide by 0 errors, we can only do that if the closest count is greater than 0. Then once we calculated that mean, we can assign it to new centroids at k and return that. And again, that will return the updated centroid positions. So let's go ahead and plot that now to see what the new positions look like. Alright, so as we can see, the clusters moved to the mean position of their closest x data points. So the red star is now at the mean of these red data points, and this blue star is at the mean of that one blue data point. But now we'll notice that this red data point is a lot closer to this blue star than it is to this red star. So let's make a change in this code right here to show that. Now, even after we updated the cluster positions once, we still need to update it again so that we can get that blue star in between these two blue points and the red star in between these two red points. So let's manually update the centroids one more time. So we updated the centroid positions again, and they are now correctly representing their two clusters. But we don't want to manually keep calling these functions over and over. So let's write a new function that does this for us over some number of iterations. So here we're going to pass in our x data points, k for the number of clusters, and then the number of iterations we want to use for updating the cluster positions. And the first step that we're going to take in this fit function is we're going to create this feature ranges variable. And this is going to be a 2D array that essentially is going to capture the minimum and maximum value of each x feature. So for example, it's going to capture the minimum and maximum of x1, which is 1 and 4, and then the minimum and maximum of x2, which is 1 and 5. And then we're going to use these ranges to initialize our clusters so that we can ensure that our clusters are going to randomly initialize somewhere inside of our data and not initialize at some point way off. So given that, let's initialize our cluster centroids. Alright, so now we've randomly initialized all of the starting positions of our centroids. So now let's go over each of the n iterations and update the centroid positions. Here we have the finished fit function. So in that final step, we're updating the centroid position to their closest x data points. So once that's done, we can go ahead and return the centroids and their closest x data points. Now let's try to use this new fit function against our x data set. So here if we pass k equal to 2, then we reach that same result. Now let's test this again, but using a lot more data with multiple clusters. Alright, so here we're creating a data set with 200 points. There's going to be 2 features, or an x and a y axis, and 7 centers or clusters, and we'll use a random state of 10. Now let's plot this data to see what it looks like. Alright, so as we can see here, we have 7 clear clusters. So to go with that, let's initialize 7 cluster centroids and see if we can fit it to this data. Alright, and at first glance, it looks like our clustering algorithm did pretty good, except if you look closer, you'll notice something a little bit odd. So this green star up to the top left is almost taking over 2 clusters, while these 2 blue stars to the top right are splitting a single cluster. Let's see what happens if we run this a few more times. Alright, and it looks like it's getting it right most of the time, but every once in a while we'll see another instance where our clusters are not very effectively identified. So let's take a look at a metric that tells us if our cluster centroids are well placed or if they could be better. Alright, and back to the whiteboard, let's take a look at how well our algorithm is placing our clusters. So we have a similar plot like before. I just moved these clusters into a little bit of different positions. But here we can clearly see that cluster 1 is nearest to point 1 and 2, and cluster 2 is nearest to point 3 and 4. So let's show off all of these distances. So here we have the distance between the closest x points and their corresponding clusters. Or in other words, we're getting the distances between each xi and their corresponding cluster. And here to show off the closest cluster index for any given x data point, we're using this c at I. And to give some more context, if we had c at 1, that would be pointing to the first cluster, because the first x point right here is closest to the first cluster. So to get a sense of how well each cluster is placed, let's get a distance for each x point and their closest cluster. And then we can go ahead and divide that by m to get the mean distance. So what we have right here is actually going to be the cost function for k-means clustering. And we can denote the cost function with a j. And in this cost function, we're using that array of the closest clusters, which is represented by the c's. And then we're also passing in each centroid position. And since in this cost function, x is actually going to be considered some constant value, we're going to pass in our C array and our cluster array. And these are values that we're going to update and try to minimize the cost with. Now to tie this back into what we looked at earlier, we said we want to repeat the k-means clustering algorithm multiple times until we find the best final clusters. So the best final cluster is going to be numerically determined using this cost function. So let's head back into the Jupyter Notebook and apply this cost function so that we can find the best possible cluster. All right, so here we're going to write a function to calculate the cost of our current centroids and closest array. So here's our calculate cost function all written out. We need to pass in our x's, our centroids, and our closest array. And then we're going to be iterating over each x data point and then calculate the distance between each x data point and its closest centroid, and then divide that cost by m to get the average distance and return that cost. And if we run that with our current centroids, we get a cost of about 1.8. So let's make a note of that. And then we'll continue running our fit function until we get a little bit better aligned clusters. All right, so here it looks like our clusters are perfectly aligned with our training data set. Now let's see what the cost of this is. So as we can see, when our clusters are better placed, we get a lower cost, and that's perfect for us. So now if we just apply this fit function multiple times, then we can return the best values for centroids and closest that give us the lowest cost. And since we're going to be using a function very similar to this fit function, we can go ahead and copy it down to right here. And the only change we need to make is calculate the cost after each fit, attempt to fit multiple times, and then return the best centroids and closest array. So let's say that we want to try fitting 10 times. Then we want to keep track of our best cost and best centroids and closest array. Now we'll fit the model n fits number of times, or in our case 10 times, and return the best centroids and closest array. All right, so for in each fit, we're going to converge our centroids, and then if our cost is better than our minimum cost, then we're going to update the best centroids and our best closest array, and finally return the best centroids and the best closest array. So let's go ahead and run our algorithm again over this data set, but we'll run it 10 times and use the best centroid positions. All right, so we ran that once and it gave us the expected results. Let's run it a few more times just to make sure that it's running smoothly. All right, so we ran that a few times and it looks like it's working a lot better with this number of fits. So now let's see what happens if we increase the k value. All right, so here we might notice that the x values are getting distributed over multiple clusters. But another odd thing to notice is that this star here is sitting at 0, 0. And the reason for that is this cluster is not assigned to any points. So by default, that centroid position is going to go straight to 0, 0. Then we can look at this next step that will remove these 0, 0 clusters that have no x points assigned to them. So this section in our fit function is where we're finding the closest x data points and then assigning our centroids to the mean position of those data points. If our centroids have no closest x data points assigned to them, then these centroids have no mean to go to, so they go to the origin or at 0, 0 like we saw below. So what we can do here is after we update the centroid positions to their means, if there are any centroids that don't have x points assigned to them, we can just go ahead and remove those centroids from our centroids array completely. So here's the change we made. We created an empty array called temp, and that's going to store all of the centroids that have at least one x data point assigned to it in the closest array. And then once we have all of those centroids in our temp array, we can update the current centroids array using that temp array. And if we run that, we'll notice that there's no redundant cluster at that 0, 0 origin. Now, one thing to mention about this update is that we no longer have k clusters. because this code effectively removes redundant clusters that aren't necessarily adding to our algorithm. So if we look at the np.unique closest, we'll see that we have less than 15 clusters now. And if we actually get the length, now we only are looking at 13 clusters instead of 15 clusters. If we run again, we get 14 clusters. Again, we get 13 clusters, and so on. Just a last thing to mention is this can take in any number of features. So let's say we had 7 features. So before we were looking at 2 features, which would be the length and the width of shirts. But now if we had multiple features, looking at multiple different aspects of either shirts or whatever other data you're looking at, then we're not necessarily gonna be able to visualize all those dimensions. But what we can see is that our algorithm is still gonna work and create clusters over all of those different dimensions. Anyway, that's about it for k-means clustering. I hope you enjoyed the video and hopefully you learned a little bit about unsupervised learning using this algorithm. If you want to see more videos like this, make sure to subscribe and like. Thanks again for watching, and I'll see you in the next one.